So, next 3 lessons, we will talk about simulation. We already talked about simulation, but now we are talking about the simulation software and the best practices. So in this lesson, we will have a quick overview of what are the simulation programs available worldwide today. And fortunately, almost all of the top packages all over the world are available in India today through some vendor. Okay. So we'll look at some of those programs. Wherever we had access, we tried to run the programs through the people who helped us to have access to the software. But what we did, and I don't think anyone has done it anywhere in the world so far, is that we took a same example and where we have the actual Foundry results. We ran the same example on all those 607 software. And I'm going to show you screenshots of those so you get an idea of how the results look like, and also you get to see what kind of results those software can produce. Some softwares do produce some additional new results, and you can take a look at how they look like and what kind of results they produce. So we'll see that in this session. So what kind of example we have taken up? We already seen a glimpse of that in the previous lesson. We took a part and we called it as our IIT benchmark part, and see the dimensions. It is about overall about I think 200 millimeters in length, about 20 centimeters in length. It is neither too small nor a too large a casting, a representative casting. The wall thickness, again, if you see, a representative of typical castings made in most foundries in India. Okay, and we put a top riser, and even the gating position is fixed. So in all simulation programs, as well as shop floor, we are scoring really or virtually exactly same casting. Now, what are the special features? If you see on one side, you have an L junction. On the front side or right side, you see an L junction. On the other extreme side, you see a plus junction. In between, you see a T junction with a thick section. These section thicknesses are not uniform. If you see in the previous picture, you have the middle wall thickness is 20 millimeters uniform, but somewhere you have a 40 millimeters, somewhere you have 10 millimeter wall. So you have different wall thicknesses, different kind of junctions. So you can look at different effects of N effect and feeder effect and junction effect. Also, we have standardized where you should put thermocouples or where you should cut a cross section and what sections you should see. All this has been standardized. Now, that idea of spending so much time on standardizing is that if any other colleges or any foundries want to use our benchmark to try and pour a casting in a different material or different process, we'll be very happy to use the data to publish that. Hopefully, I'm thinking in a year's time, if you and your friends and other foundries cooperate, can we have a book of just this benchmark casting poured in different metal process combinations? And we capture the data of thermocouple data and all that, which will help us to generate the thermophysical data which is required to run the simulation programs. Not AutoCAD as much, but many other imported programs require the thermophysical data. Okay, that we can start generating, and hopefully we'll help out in that way also to the community. Okay, so what are other parameters? What I'm showing you now is going to be an aluminium. Although one last example I'll show you in iron also, or ductile iron. So this is green sand molding, and aluminium, because for academics, aluminium pouring is much more easy than steel pouring or iron pouring. So we use aluminium as a benchmark. So you see the pouring temperature and pouring time. Then we also see methods parameters, feeder and feeder neck and gating design, screw, runner, in-gate, whatever. The mold box size, the total casting weight, all these are known values. First thing you can do is to, in the simulation software, compare these values with the geometry values, weight of the part. Okay, because density, volume, weight, all of them can be checked immediately. Now this part again made with a centralized screw and 2 gates with 2 cavities. It's a 2-cavity system. And the advantage of that is that in one we can put thermocouples in one or both cavities. So we can capture different temperature values or temperature history in that way. And we also see a cut section showing exactly how the defects look like and where they are. So you can see shrinkage happening in the feeder, in the neck also somewhat, and also extending into the part itself. And if you see more carefully, the shrinkage in the part is extending, just ending just above the bottom of the thick section. Now in most of the physics-based programs, or let's say programs based upon the numerical methods and FEM and FEM which you mentioned, you do need the IHTC value. Now different programs have different IHTC values as tables, or graphs, or charts. So we can't compare apples with oranges. So what we've done is we also try to standardize the IHTC value also given to the software. The other IHTC value is the heat transfer coefficient from your mold to the outside edge. the convective coefficient, which were taken as 10. Okay. And then the mesh size also has to standardize, because mesh size will affect your computation time and accuracy. So we standardize as 2 millimeters, which is 1% of the part size. Part size is 200 millimeters. The wall thickness, minimum wall thickness was about 10 millimeters. So this is 1/5 of that. Very safe. So we cannot have any errors in the computation. And also mold wall absorbs heat. So minimum mold wall thickness, if you remember from our earlier conversations, minimum should be about more than twice the wall thickness. So our wall thickness minimum is about 20. If you look at the big thick section, it's about 40. 40 into 1.52, 70 millimeters all around. But on the top anyway feeder is there, so we don't worry about the top wall thickness. So 70 millimeter again makes sure that mold is able to absorb all the heat. So all parameters taken care of in the design of the thing. Additionally, I showed you in the previous lesson, we need other various inputs. What is the pouring temperature, what is the filling time, so gravity, direction, and how it is placed, ambient temperature, and few other parameters also are in this slide. But previous what I showed you, the critical ones, these are additional parameters. With these, we are able to give inputs to almost any simulation package available in the world today. Now, which package we are talking about? This is a, I think, fairly exhaustive list of packages available today. I don't think we have missed any package. If you think you know any other software which is available, but it's not listed here, we do tell us. But I think we have taken care to ensure that everything is there. So you see AdStefan coming from Korea. Then you have any casting coming from Taiwan. Okay, these are all new entrants. These are all not there before. Then AutoCast from India. Then you have CapCast from developed by Chinese in USA. Okay. Then we have CastCE, which is developed by a Finnish person called Arno Lovo. Again, one of those old packages. Then Flow 3D comes from a very respectable group in USA, which is Flow Science, and they have, in fact, that's one used for many other simulations also. One of the most well-respected academic packages and scientific packages, also now available for casting simulation, flow and solidification. Although it says Flow 3D, it can do solidification also. Then you have MagmaSoft from Germany, Mavis from UK. This academic package didn't really get commercialized too well, but it's available somewhat in the local industry. I think now I heard they have stopped marketing this. Then NovaFlow and NovaSolid, both coming from NovaCast in Sweden. Then we have Procast, originally from USA, developed by American, working in UK. Later on, it is picked up by French and Swiss people. Now it is owned by French and Swiss companies. And then we have Softcast, an earlier software, DOS-based software from India. Then you have Sootcast from Canada. Virtual casting from, I mentioned this group of three ladies in Trivandrum. Now we just start seeing some results of packages which you have access to. So as you can see, this package you can see the defect, the hotspot in the feeder mainly. You can see also hotspot extending into the neck, and also you see a bigger hotspot in the casting. So and that more or less corresponds. The big hotspot exactly more or less ends at the little above the bottom of the thick section. The feed paths actually give you much better picture, and these are few feed paths. You can also generate more dense feed paths. You can see again they are converging in the thick section, also stopping in the neck, also stopping in the feeder, and the entire line, as you know, we got the shrinkage defect. And also it can interpret the results automatically for a metal process combination. Again, you see the shrinkage shown in all the three areas. The flow simulation, you can catch some additional results, like we talked about gate velocity, impact angle, and you can calculate momentum from that, the vertical velocity from which you can look at blowholes and maybe top misruns. Okay, all these things you can capture from the. It is a simplified flow simulation. It is not like the splashing and things like that which we talked about earlier. The splashing simulation takes far more time to compute. So this is like, again, Indian way of doing something which gives you good enough information to optimize your gating system and catch some major filling defects like your inclusions and maybe air pockets, but it won't give you the streams merging, and cold sheds and misruns are a little difficult to predict by this. So this is a simplified flow simulation. It's almost real time. But if you spend 10 hours on a Navier-Stokes equation, you can get coupled simulation. This is not coupled, it is decoupled. And decoupled is good for thick castings poured in under gravity, or thin castings poured in a hot mold like investment casting. So we can handle those two. which covers most of the gravity and casting processes. Then we have flow 3D. I was mentioning this from USA, and here you see clearly again two hotspot areas, but here you see a bigger hotspot solid fraction coming in the casting portion. You see a smaller one in the feeder, which is slightly reversed of what you see in the actual casting. And this is your temperature also is showing higher temperature in the casting than the feeder, which is as mentioned slightly reverse of that. Now air entrapment you can look at, volume fraction of air. So the volume fraction, when you say you're talking about in a cell, when you say a mesh or cell, how much fraction of the cell is occupied by solid, how much by liquid, and how much by gas. So we're able to display three different volume fractions. If you show only liquid, it is your flow simulation. If you show solid, it is your solidification and porosity and all that. And if you show gas, you can start looking at where blowholes can form. So you have three kinds of things here. Surface defects. Then we are looking at the other American software called Procast. Now it is, I told you, owned by French and Swiss people, called ESI. Filling simulation, what you're showing here, the filling in seconds. So red is the at the top, which means red areas fill last. The red doesn't mean hot. Red only means here which areas got filled last, okay, and the blue got filled first. Then solidification, here also you see the temperature, which solidification time, which areas solidified last, and you can see around the feeder you have the longest solidification time coming up. Again here it's interesting, you are seeing hotspot or solidification, last solidification only in the feeder, not in the casting. But if you see solid fraction, now you see the entire picture, the entire feeder to neck to casting, the solid fraction which indicates the first indication of your shrinkage porosity is coming in this picture. And center of that you can see is a more or less corresponding with your shrinkage cavity. But when you actually ask you to display the actual shrinkage, maybe you have to adjust the metallurgical model a little bit, so you see shrinkage only in the feeder, you don't see shrinkage in the neck and in the casting. So many of the software, remember, although we have been using them and we know the scientists were using them for 2-3 years, even we have difficulty in knowing how to fine tune to get the right results. So I know that we have to manipulate a little bit some coefficients values, but we really don't know what to do to get the results to match the actual results on shop floor. So I know that something is wrong here, but wrong may not be wrong with the software, maybe we don't know how to use the software. I mean I'm putting blame on myself here, but you should supposed to see the shrinkage, you know, through the casting and the neck and the. Now this is an interesting result, velocity vectors, where the flow velocity is high and low. So again if you see most of the velocities are in the blue area. Now the violet is really low, but then the blue is little higher velocity. I can't say anything more than that, maybe it is inside and I cannot visualize it carefully, but you can see where velocities are high and low. Solid cast is again one more American package where it's one of the most popular packages in America with several hundred installations, and originally it was sold by AFS, but later on they privatized that and it is now a finite solutions. So you can see here one more interesting result, which is temperature in the casting as well as the mold, which is possible to generate if you extend the computation to mold also. And solidification time, so you see the feeder solidifying last, the yellow area, and a thin section solidifying first. We mentioned Niyama criteria, we said G by root R, okay, and if G by root R is low you start getting a shrinkage, especially centerline shrinkage, it is good for centerline shrinkage. So you see Niyama criteria value, again yellow there, which is one indication of shrinkage porosity. Vertical velocities, this is the first package where we see vertical velocities captured, okay, apart from AutoCast. So you can see I think the highest velocities are at the bottom, and it's at the, blue is actually -5, right, so it is actually low, and then red is actually high velocities. So whatever it means we can capture that. Now virtual casting is from Trivandrum, NIST, and they have some more interesting results. They are able to generate cooling rates and cooling gradients. Cooling rate also is important criteria. So if I can somehow add this to my the original computation, so if we can get temperature and gradient, which we can get in AutoCast, but now we are looking at collaborating with this group to get the cooling rate also. So if I have all the three values, temperature, gradient, cooling rates, I can now capture almost every defect in the foundry, including cold shuts and hot tears and things like that. Temperature, and again here you also can see a good result, fairly good result, where you can see the middle neck area and above and below neck is hot, and solidification also is fairly consistent with what we have seen earlier, the actual shop floor results. And again, this is the porosity in the feeder is being seen as a sink here or a pipe here, but the porosity in the neck end casting is all right. Okay, so it's matching with the actual observations here. Now we also had difficulty in getting access to magma, but we finally got an iron foundry to look at that. So remember, I am showing you results for iron casting here. Is iron or ductile iron? Ductile iron here. Okay. So you see now the cooling rate, which is what you have seen also in the previous virtual casting, and hotspot now you see only in the thick portion of the casting. I do not know why we don't see hotspot in the neck and the feeder. Feeder obviously is bigger and thicker. So again, I do not know what inputs we gave wrong that we are getting wrong results here. But you are supposed to see hotspot, bigger hotspot in the feeder and then neck and the casting. And modulus also, which AutoCast also does, and here also you can see, you see the largest modulus in the thick portion of the casting. And liquid to solid contraction again, which is in the beginning of the solidification. Pictures will be same. So you can say in one line, all of them can predict solidification reasonably well, although in some packages the shrinkage did not match with the actual shop floor, but that could be perhaps because we do not know what inputs to give to software packages. And in terms of time, you can see that they take anywhere from a few minutes to maybe few hours. So you have to spend at least about a day to get the results from solidification. Now flow is a different story altogether. If you're talking about coupled flow and solidification simulation, it can take up to 5 days. For this particular part, maybe it will take about 2 days, but for an engine block, you can start the program and just take a long vacation, long Dasara vacation, 7 days, 10 days, then come back and take a look at the results. It takes that much time really. Okay, so that is a summary of your quick overview of the software available today worldwide, and some glimpse of the output and results from these packages for the same benchmark part, which we have standardized to make sure that we can compare across the packages.
Between FEM and FDM, which is better?
Okay, so FEM stands for finite element method, FDM stands for finite difference method, and FDM and FVM, which is third one, finite volume method, have a similar way of dividing the casting, which is like bricks. If a complicated shape, you can't calculate the equations for a complicated shape, you break it down into cubes or bricks. And FDM and FVM both are brick kind of subdivision. The FEM, finite element method, typically divides the casting into tetragrams, which is like pyramids. And all pyramids need not be of the same shape or same size. So the advantage with FEM is that you can, if you have a curved and complicated geometry and thin walls, you can better approximate the geometry of the part with a fewer number of elements, because you can have any angle and shape. But bricks will always give you a step kind of a structure, and steps means what you're simulating and what is actual casting is quite different. So unless you make a very fine, very thin, very small brick, you are not approximating the right thing. So in investment casting or pressure die casting, it becomes very important. So we say that usually it's a good idea to use FEM, which is tetragon elements, for thin wall complicated shape castings, and you can happily use FDM and FEM for thick wall casting, and thick wall casting is good enough, it need not be simple shape. The other difference between these two is that, and I mentioned in passing earlier, in FDM the mesh generation, dividing casting into those bricks, is completely automatic and fast. A user doesn't have to worry about it. In FEM, the division of casting into those tetragrams is not automatic, it is not easy, it is error prone, and sometimes you spend more time than simulation to fix the division first.
AutoCast simulation software, we may use it for each type of casting, like pressure die casting, centrifugal casting, and in different type of castings we may use it.
Okay, you meant processes there. Okay. As far as certification is concerned, AutoCast can be used for any process, including pressure die castings, LPTC, we have used it happily. But when flow is concerned, I mentioned that we do a simplified layer by layer flow simulation and not a Navier-Stokes kind of flow simulation, where you can capture velocity vectors in all directions. You can only capture the projectile motion of the metal coming from the gate and vertical velocity of metal rising in the mold, which is good for gating design and some basic defects like inclusions and maybe air entrapment and venting design perhaps. The vendors of almost all the packages, all of them have India office, they have Indian partners, so they are all available in the country today. And because India is a big market, a big foundry market, so they are all here, they are all competing with each other, so thanks to that the pricing is very good. So thanks to competition between the vendors, you get a good deal now.